I'm Dylan Cook, and I'm here to present a research project that we did in astronomy class. It's about pulsar stars, and I'm about to talk about the methods that we used and what the data concluded. Obviously, what a pulsar star is a rotating neutron star that emits focused beam of electronic radiation that is only visible when standing in its pathway. What a neutron star is when the core of a massive star undergoes a gravitational collapse. It condenses down to about 20 kilometers in size, and the weight of this star is astronomical. To compare it to something else would be like 1 sugar cube size of material of this star is equal to the entire weight of Mount Everest. So you can obviously see that that is a very dense star and has a lot of weight. How we did this experiment, and we used the Vireo program that was able to observe radio waves that were emitted by a pulsar star. And just to explain on how we did this, basically these were the waves at the pulsar star. The frequency, as you change the frequency, you got different rates at which the star emitted radio waves. As you change the vertical gain here, you'll be able to see more waves as you go up in gain, but they're less distinguished. So if you get way too high, you're not going to actually be able to see the difference between this and this. They'll just all blend together. The same with the horizontal. As you go up in seconds, the more pulses you get, but the longer you expand it, obviously you're going to lose definition of the wave itself. And then the added channel, basically what the added channel does for you is you can take a look at a frequency of 600 here and then change it again to a different frequency and compare the wavelengths and how fast the pulsar is pulsing when you do that. So it does change the rate in which the pulsar is pulsing. The first result is of a pulsar, it's 0628 minus 28 is the number for the star. And the frequency 400, you can see it was at 1 second when it very first pulsed, and at the last second it was at 3.45 seconds. And as you go up in frequency, it goes a lot faster. Once you get to 600, you're at half a second, and once you get to 800, you're at 0.3, and to finish it up, you're at 2.94 for 600 frequency, and the last pulse on 800 frequency is 2.8. Like I was saying before, with the added channel, it allowed you to look at different frequencies. So this is 400, 600, and 800 of the data that was just shown. And you can see at the very first pulse was 1 second, and then it goes down to a half a second, and then down to 0.3 of a second. And you can see how the rate changes with the frequency. This is a different pulsar star. This is 2154 plus 40. With this star, it was a little different. The frequency at 400 was 1 second, 1.3 seconds. The frequency at 600 was at 0.29 seconds. And then at a frequency 800, it goes back up to 1.49 seconds. And this is the data for this star. So as you can see, at 400, it's pretty quick, and then at 600 it kind of slows down, or goes a little bit faster actually, as you can see the first pulse here and then the second. And then once you hit 800, it actually slows back down, and that's probably because you're losing that first pulse that would be over here that you're not actually going to see in this frequency. So that's why the frequency mattered so much, so that you could see how many pulses are in that section. Pulsar, the data concludes that the pulsar 2154 plus 40 was at a faster pulsing rate than 0628 negative 28. The faster pulses are younger stars. So as the star ages, it continues to spin. That's how you get that pulse effect. And as it spins, that's how you get the light. And when the light hits, it looks kind of like a lighthouse effect. And as it gets older, obviously it's going to slow down the spinning effect, and eventually it will stop. Obviously that's billions of years before it ever would stop. And so that's basically what we were trying to find out, was which star was younger and which one was the older one. and looking at the information, 2154 plus 40 was the younger star out of the two that we looked at. Thank you.